So this James Webb Space Telescope catches sight of a rare star on the brink of going supernova. This is sciencealert.com. New image from the JWST. We will look at that later. There's some other pictures that I would like to show as well. Star WR124. Only certain stars turn into wolf riots. In just a few 100,000 years, is going to explode in a glorious supernova. Wolf riot stars can be some of the spectacular. They are very hot, very bright, blazing away in a last stream of light at the end of their main sequence lifespan as a fusion fuel. That's the image right there. You can see it's just about to blow. That is a really cool image to see. Because you can see all the gas getting shot out from it. Because it's getting towards the end of, when it says fuel, it's getting towards the end of, I want to say it's hydrogen. I believe at the core is hydrogen. I do not have this in front of me, but I'm going to say that it will pull all of the fuel, the majority of the fuel, from the hydrogen that is at its core. And some things later is what you'll see is, depending on the size and the supernova explosion, different things happen. So that is something to keep in mind. Significantly depleted in hydrogen, but rich in nitrogen or carbon. They are losing mass at a very high rate. Mass they lose is also high in carbon, which absorbs radiation, re-emits it as infrared light, which is something that James W. Space Telescope can see. And makes us say that there. There's another one. Hubble Space Telescope. This is 2015. Very, very cool. Now let's go over here. Look at this. Here's the Mary image. Mircan and Mary combination. Why is this website not working? I was just using. All right, I guess we'll have to skip that. That was not working, but anyways. Speaking on supernova, a supernova is the biggest explosion that humans have ever seen. Each blast is the extremely bright, super powerful explosion of a star. All right. So now let's get into what a supernova is. One type of supernova is caused by the last hurrah of a dying massive star. This happens when a star at least 5 times the mass of our sun goes out with a fantastic bang. So it's a much bigger star than our own. Because our sun most likely won't. I don't think our star will go supernova, but I could be wrong. Could be wrong. And so here's what I was saying earlier about in terms of hydrogen fuel. Nuclear fuel at their cores or center burned. It's very hot, generates pressure, and then that pressure is what is pushing out. As you can see with these red and blue lines right here. When a massive star runs out of fuel, it cools off. This causes the pressure to drop. And the star suddenly collapses. Because you got to imagine, once the fuel's gone, there's literally nothing pushing out the edge, so it just kind of rushes in. Imagine something 1 million times the mass of Earth collapsing in 15 seconds. Yikes. The collapse happens so quickly that it creates enormous shock waves that cause the outer part of the star to explode. Usually a very dense core is left behind, along with an expanding cloud of hot gas called a nebula, a supernova of a star more than about 10 times the size of our sun may leave behind the densest object in the universe, black holes. Yep, you need a big, big star to get a black hole, which there are plenty of. When it comes to these supernovas, these things are pretty big. So I just want to continue to move on. And this is a Wikipedia article that is just all about supernovas. It's a powerful and luminous explosion of a star. All of this stuff, different types in terms of sizes and all this kind of stuff. Core collapse. This is one thing I wanted to touch on. So these would be the potential layers of a star when it's at the end of its life. And as you can see on the outside, I believe hydrogen, helium, carbon. I think that's no, that's iron. Neon, oxygen, silver, maybe, and then iron. Or is that gold? I'm not sure. Do not remember. All right, let's see. Okay, here it goes. Concentric cells of hydrogen, helium, carbon, neon, magnesium, oxygen, and silicon are burning inside the stars. Iron, yes. So the core is made of iron. Okay, so the hydrogen is going to be the first thing in the star, the early parts of his life. Didn't mean to do that. Here we go. And then through nuclear fusion, not fission, but fusion, which we have not been able to do on this Earth, which is where you take you're fusing nuclear atoms to make to produce energy and also make new particles. So that first core will be hydrogen, and then I'll push out the helium. Through fusion, it'll make helium, and then helium will go to carbon, then neon, oxygen, so all that stuff, right? And so as you can see, the earlier parts will be on the outside because that's where the core will start. And as it goes, it creates all of these atoms. And then once it explodes, those atoms go flying everywhere, which is what I kind of wanted to touch on here. The elements created, because this is something that's really cool. And we got super lucky in our specific area because, I mean, if there wasn't a supernova around us that gave us these elements, we would not be here right now, because some of these elements do help create life as we know it on this planet. Supernova are a major source of elements in the interstellar medium, from oxygen through to rubidium. Though the theoretical abundances in the elements produced are seen in the spectra vary significantly depending on the various supernova types. Type 1A supernova produce mainly silicon and iron peak elements. Metals such as nickel and iron. Core collapse supernova eject much smaller quantities of the iron peak elements than type 1A supernova, but larger masses of light alpha elements such as oxygen and neon, and elements heavier than zinc. The latter is especially true with electron capture supernova. Type 2 supernovae is hydrogen and helium.
Heavy elements are produced by nuclear fusion for nuclei up to silicon. Yeah, so it creates a bunch of stuff. Big Bang fusion, hydrogen and helium. And then look at all of these. Exploding massive stars. So the yellow goes all the way up to RB. So, and also all of these other ones right up here, you can kind of see how those are created through certain circumstances. Merging neutron stars creates a bunch of these really um complex ones. So yeah, a lot of cool stuff and a lot of things right there. And it is cool to think about. Um it is cool to think about that some of the elements there are so crucial to life here on this earth, and we are extremely lucky that things worked out in our favor. All right, March 25th. I don't know if anybody else saw this, but I did. This was very cool to watch, very cool to see. Yes, just wanted to touch on that.